this webinar about X-ray 3D tomography, and we're gonna record this, so please be aware of that. And yeah, please keep your microphones turned off. And if you have questions, you could put that into the chat. So then we will take all the questions later on in the end. And yeah, I think with that I would start without further ado. So yeah, so I will have a little bit short welcome here now, and then Tuerdi gonna present himself and give an introduction to X-ray tomography and how it can be used in industrial applications. And then we have an invited guest from Exciscope, Lars Romson, who gonna talk about the next generation X-ray microimaging. And then Helena Björk from RISE gonna talk about RISE battery analysis lab. And then we hopefully have 10 minutes for questions and discussions in the end. Then I move on. Okay, so yeah, a little bit the background here then. So we have an initiative for large-scale research infrastructures at RISE, and it is both with neutrons and synchrotrons, so both X-rays and neutrons. And the reason for that is that they complement each other very well. And it's all about understanding materials at different length scales, so from millimeters down to angstrom, basically. And then our vision is that we want to help to support and strengthen the industrial competitiveness by being a leading partner for this in terms of applied research and development and these large scale infrastructures. And the mission we have at RISE is that we should help industry to get access to these techniques and the competence needed to work with it, and also experimental environment as these facilities. And how we would like to do this is that we would like to integrate X-rays and neutron techniques in our toolbox to facilitate this use in business projects and in applied research. And we hope to be able to offer the whole value chain for industrial research, all the way from problem formulation, measurements, interpretations, and to the solution for our customers. So that is our missions. And as we see it, there is a lot of benefits for basically all types of industrial sectors. So just mention a few here. So you can imagine that if you develop a new drugs, then you would like to understand the structure of proteins, for instance. If you're dealing with foods, you would like to control, for instance, where the salt are in the salt reduced foods. Dealing with packaging materials, it could be all about understanding how the liquid is taken up in the packaging materials, for instance. If you're working with engines, it could be about cracking in cast iron during load. And if you're working with recycling, it could be about detection of low concentration of toxic substances in ashes, for instance. So it has a broad use in many different industrial sectors as we see it. And then our claim is that the synchrotron X-ray really boosts the development here. And it complements a lot of things that we are already doing at RISE. So all our other advanced techniques, it complements very well. And we also have lab-based equipment, and we have done the synchrotron access. And what we hope is that it should give new possibilities in terms of material research. So that could be everything from developing new, more efficient processes. It could be new materials with new properties, increased flexibility in material selection, for instance. But it could also be that it relates to future challenges regarding circularity and so on. But the base is really to get deeper understanding of the materials. And that could also help to enhance trainings at the companies of visualization of the challenges that they have. And I also would like to mention that it very nicely complements our other advanced techniques that we have at RISE. So that could be anything from NMR techniques or other techniques. So for instance, we have a new cryo-TM at RISE, which is very useful in complement to these techniques. But we also have very nice lab equipments, as you see on the pictures here. So we have a very nice lab wax instrument in Stockholm. And then we also have nice X-ray tomographs in Stockholm. So for this is Vei and Malte that are responsible. And Malte sent me 2 pictures where he had image like a wasp that you can see on the right side here. But of course, we have many other techniques that these complements very nicely. So I think it really fits nice into the toolbox that we have on RISE, at RISE. And what are we doing in this initiative? So we have a lot of activities. So that could be that we are making joint research projects together with different parts of RISE, but also that we are doing with universities and so on, and companies. And then we hope to be able to strengthen our portfolio of techniques that we can use in business projects. We go to synchrotrons to do measurements. We have Big Science Sweden that are developing really the facilities. So that is a big program, really excellent program. And then we also would like to educate our colleagues. So that is what we're doing today. So we educate application experts, and we have a user community. And then I would like to emphasize a little bit people that are involved. There are a lot of people involved, but I'm very happy that we have a group of technical experts, as you can see here, that are really have the competencies to go to the synchrotrons or the neutron sources to do experiments, and that could help you to get access to these techniques. And then they are supported by their unit managers, where the technique experts are. So I'm very happy that also Tuerdi joined this team now. So you're going to learn more about that today. And then we have a project group that reach out. So you have Björk from the competence or the competence platform about advanced techniques. And then St. Christian is leading the Big Science Sweden. You have Camilla working with soft materials. And we have Fredrik working with business development, and Jessica as a communicator. And then we also have a steering group that is supporting us in all aspects. So Pernilla is the project owner, and Monica and Anne and Marie is supporting in the steering group as well. So if you're interested in using any of these techniques, please feel free to contact any of the people I have mentioned here. And I'm also the project leader for this, so I'm certainly one of the ones you can contact if you have more questions after this. So with that, I would like to, without further ado, I would like to invite Tuerdi to give his talk about both himself and a little bit the introduction of X-ray tomography and its use in industrial applications. So please, Tuerdi.
Thanks. Yeah. Thank you, Niklas. Hope you can see the screen. Yeah, in a right mode.
Yeah, it looks good.
Okay, thanks. Big thank you everyone for joining in this seminar. So as Niklas mentioned, my name is Tuerdi Maimaitiyili, and I'm originally from China. And I have a material science and engineering background by education. So I did my both master and PhD in the field of material science and engineering at the Malmö and Lund University, respectively. In my earlier times, I used to work with softer materials like the bones, papers, aluminum foils, but later on more focused on the engineering materials. My PhD was all about understanding the hydrogen embrittlement phenomena in zirconium alloys used in nuclear power reactors. And since the work was more focused on the understanding the phase transformation, existence of the phases, determination of the crystal structure, etc., I was worked a lot with the in situ, ex situ experimentation at the large scale facility using both synchrotron and neutron techniques. So after PhDs, I continued to work on hydrogen embrittlement, but after I started working also on additive manufacturing of metallic materials at the Malmö University as a postdoc. Then moved to Switzerland and did another postdoctoral research work at the Palscher Institute, where I was involved on project developing sample environments and also developing a material characterization technique for additive manufacturing and advanced material processing using photon and neutron sources. Then moved back to Sweden in 2019 and joined the Swedish Metal Research Institute Sverige as a research specialist. And my role there was mainly supporting and leading applied research, which involves large-scale facility-based material characterizations. And as Niklas mentioned, from last month, I joined RISE as an imaging specialist with a focus on tomography at the large-scale facilities. So this is a bit of a short overview about my education and research background. And now I would like to show some cases which I did during past research. This is one of the in situ devices which I've been involved in developing while I was at the PSI in Switzerland. This is how the system looks like. It's basically a small 3D printing machine for metallic materials. So it can allow us to work with the transmission and reflection setup of the X-rays or the neutrons. Then we can able to do a scattering imaging experiments. And this particular example was done at the diffraction setup in the transmission. This illustrations for the reflection right now. But we can, with the help of this kind of instrument, we can follow what's happened during the solidification, and also can able to understand how the laser powder interactions, melt pool dynamics, etc. And then that will be fed into other complementary studies in the conventional means. So it will give us a really possibility to get the good information about the development on the material. Then I also did some works related to imaging using conventional tomographies to understand the inclusions and the defects in the steel as shown here, but also using a neutron tomography to looking into a stress-induced phase transformations on high-strength steel during mechanical testing. And also in the more ongoing projects where I was supporting the PhD students in Uppsala universities doing tomography and XRD-based works to understand the mechanical properties and the microstructure relationship, as well as the additive manufacturing processing and post-processing conditions. So those are something related to the imaging works, but since I also work with the neutron a lot, that I also did some works related to this Bragg edge imaging, which is slightly different compared to the conventional tomography, but it works in similar manner. But we use this technique to look into stress distributions in bulk materials, like as shown here. And this is how the result looks like. And since we worked with the polycrystalline materials, the texture is quite important for such materials to understanding anisotropicity. And I also did some works, both using neutron and X-rays to look at the bulk textures in the material in connection with the residual stresses. And lastly, that a lot of time was spent on developing data analysis toolboxes, libraries, and software for dedicated applications, so have some background in the program development as well. So this is very short, and this is where I think I lost my pointer. This is where I come from, and there's just somewhere I've been worked and where I lived. So very nice, happy to join RISE, and this is all. Thanks. And now I will close this and share another slides. By the way, that I cannot able to see this all the participants. So if you have a question, please write it down, and then we can take it at the end. Okay. So in the next 20 minutes or so, I will give a very brief introductions about the tomography and its industrial applications, while having a short stop at the LSRI-based imaging techniques with some industrial case examples. So before start, we should see the root of the CT, which is originated from the clinical CT, which is something looks like this in the modern days. And if you look at the inside of the CT systems, it's basically consists of a detector in one side and the X-ray source in the other. And while it started to working, the patient on the table will sliding slowly into in between those two systems, detector and X-ray sources, and then it will collect the multiple shadow images. Then that will be using back projection algorithms to reconstruct into cross-sectional image, and then it will reconstruct into such models of the scanned object, in this case, the body. So it was very good techniques, and the ability of giving this non-destructive slicing possibility for the measured object made it in very popular. And then it's not only in the medical field, but it also find wide applications in science community, specifically more in the material development field. And now despite that the old systems, or even now in the medical scanning, we have resolutions of 0.1 millimeter resolution, but now it's a commonplace to find scanners with the capability of measuring nanometer resolution from the lab or the LSI facilities. It's quite widespread, and almost all the big producers and also the lab facilities have such capacity. However, that even though we have such a large pool of options, none of the facilities or the systems can do all types of measurements in one places. All of them have some specialities and advantage, and they are quite unique by own means. But almost all systems shares these three main components. One is the X-ray sources, and other is the sample stage, and then the detector. And in all cases, they collect the image from the multiple angles from 0 to 180 degrees or 0 to 360 degrees. And like this type of 2D shadow image or the projections will be collected. Then that will be reconstructed back into a 3D rendering or a 3D representations of the measured volume. Then it will be using image processing to extract all sorts of quantitative information. And considering that technically easy and also economically more cheaper to rotate the sample rather than rotating the X-ray source and detector in the science field, that the CT systems more oriented on rotating the sample. And this is one of the imaging beamline, how it looks like at the large-scale facility, at the DAISY facility in Hamburg. So this is a table, and the sample will be placed, and it will rotate. This is just a very short description of how the system works. So for simply put, that the tomography is a non-destructive technique, and we don't need to prepare, almost no preparation needed for the sample, and it can have a possibility to collect information from the millimeter resolution to a nanometer resolution. Since it's a non-destructive, it really gives the possibility to do a correlative imaging, where, as illustrated in this example, where the battery can be measured in a micrometer resolution with the CT, and then identify some interested area. Then it will further image it with the nano CT, and then pinpoint some problematic areas. Then that can be measured with the other complementary techniques like EDS or the TM tomography etc. So really gives extra dimension and makes the material science and investigations faster. And last but not least, that this sample environment of the tomography measurement is a big plus. That on contrast to the other techniques, there is no vacuums, and which makes the sample environment development much faster and easier. Because of all those advantages, this CT became quite popular in various sectors. As shown like this here, the quality control in the additive manufacturing, or the investigation of the battery performance or integrity, and also the elemental analysis in the battery elements, or the fracturing behavior of the composite materials, fatigue cracking in the titaniums, or the cellulose fibrous materials, and the food science. And even this cases is just from the ice cream, and there is not so much techniques can help to see such kind of materials. And last but not the least is the archaeological samples together with some geological specimens. So simply put, that almost all materials and all industrial sectors can have a benefit, can get the benefit from the CT measurements. So now the question is that why we need LSRI. With the lab systems, we already can get the nanometer resolution, but why we need it? So the simple answer lies in this diagrams, that when we look at this brilliance of the X-ray sources in comparison to the lab sources, it will be immediately clear that basically at the large-scale facility, we have so much X-rays for collecting, performing the experiments. And not only that, of course, that the coherence or the possibility of energy selections, selecting monochromatic beams for measurement is much more flexible and easy at the large-scale facility. So it makes the experimentation much faster and better. And in addition, that the open design at the large-scale facilities like this one, this is basically the detector here and the X-ray coming from this side, and we have the stage in the middle, which allows a person to do easily, relatively easily, to develop more sample environments and integrate at the beamline. So it have a higher flexibility. So this is why we need LSRI facility for testing. And the advantage can be further visualized by this diagram, which shows the published results from 95 to 2020 from the synchrotron and the lab sources, the temporal resolutions against the spatial resolutions. So if you look at here, that it's clear that the synchrotron can provide much better time and spatial resolutions. But of course, that none of the lab scale facilities works in the same way as same way as the lab system. We cannot just run into labs and perform the experiment. All the facilities are shared by the science community. So there is always a huge demand for the use, and it needs a careful planning. A good thing is that there is two ways of access for such facilities. One is the so-called academic access, which does not need any fees, but based on a peer-reviewed biennial application. And another one is a much faster and flexible access, which is paid beam time access, which comes with the cost of 7,000 to 8,500 SEK for per hour usage. And the experiments commonly benefit are something which requires very high resolutions or dynamic capabilities, and something which really needs a screening and a fast data acquisition are highly benefit. And now I want to show some selected cases. The first one is this, where we're looking into the cracking in the additive manufactured steel using both micro-CT and X-ray diffraction to map up the pore distributions, cracks in the material, to really connect how they are related. And this type of experiment is considered to be very simple, and this type of work can be done in the lab quite easily. But one thing unique in this case is that if you look at here, that the total samples measured in this case is 32 samples, and the diameter of the specimen for the tomography work was 1 millimeter, and for the XRD cases, it's 3 millimeter. So if we try to measure 32 samples with this kind of a resolution for both tomography and the XRD, this will take about several months of measurement if we want to aim this quality. So you can see that it really benefits in the high batch screening. And the second example is from colleague Torsten Högren. He and his collaborators, what they did was this mechanical testing of cast iron parts at the so-called 3D XRD, together with this using digital volume correlation to look into the microstructural evolution in connection with the porous precipitates and also the grain structure in the material. Not only that, but they also extracting this three-dimensional strain maps of the specimen in relation to applied load. So it's really like a dream type of experiment for mechanical testing. It gives a four-dimensional perspective. And last thing that, as mentioned before, that the sample environment and the fast measurement is a really big advantage of the LSRI. And this is an example from the work done by Niklas. And in this cases, what they did was they modified a commercial Electrolux micro-oven to make it suitable for X-ray measurement. And then they did this in situ bread baking to follow how different ingredient of the bread and also how different baking condition will lead to different types of microstructure. And in each cases, they collect the image in 400 microsecond time. So it's a sub-second kind of imaging, very fast. And all cases, they measured 3 places in the every measurement point, and total 1,500 volumes they analyzed. And at the end, not only extracting this microstructural information, but they managed to quantify, to identify the relationship of different baking and ingredients on the baked bread. So really helps to understand and speed up the development on the science. And since you already noticed that when we say this large measurement volume, it's sorry, this brings the new topic of the limitation and the challenges. And normally at the large scale facility, especially in the high resolution measurement, each scan will take about 60 to 120 gigabytes of data just for the raw data. And when we started to analyze, it's already multiplies and grow quite significantly. So data size is quite a big concern. And the radiation dosage is also a concern for some biological materials and specimens. And when we say that the resolution, there is some trade-off with sample sizes. It's not possible to get the nanometer resolution from very large samples. There is the opposite relationship. So we need to be compromised. And then we also cannot put the very large samples. It needs to be, the X-ray needs to be able to penetrate from the sample. So we have also some size limitations. However, there is always a way around to do the experiments, and there is a huge potential. And we at the RISE have me and other colleagues, which Niklas showed earlier, can help with any questions or problems. So if you have any questions, you can should. And you can also see this LSRI page at the RISE for more information. Thank you.
Okay, thank you, Tuerdi. We are in very good time, I think. So maybe we could open up for a few questions already now. If you have some immediate questions, you can to Tuerdi. We can take one or two of these before we leave the word to Lars. Is there anyone having questions for Tuerdi or me so far? Okay. No questions so far. So then I would like to thank you for this introduction and presentation of yourself, Tuerdi. So very good. Thanks a lot. And as Tuerdi say, I mean, if you have questions after the seminar, please feel free to contact Tuerdi and others. So we then, without further ado, I think I will leave the word to you, Lars, to present the excellent work you're doing in developing a new tools for lab sources. So please, Lars, the floor is yours.
Thank you very much, and thanks for inviting me here. I will try to share, see if I can get this going. So did we get it up in present mode?
Yes, it looks good.
Fantastic. Okay, I'm Lars Romson, CEO of Exciscope. We are, you could say startup, but we believe we are a scale up now. We delivered 3 instruments last year to different universities, and we are on our way to deliver more. We are sprung from KTH, Applied Physics there, a team of 3 PhDs and Professor Hans Hertz started this company in 2019, and I joined pretty much around then in early 2020, and in 2021 we've built our first in-house system. And as Tuerdi very much said, when we do lab-based instruments, we cannot do it all. So we have targeted for low SED, that could be translated to low density materials, and fast scans. And we could see this as we move synchrotron performance to the lab. We don't have it. It's much faster, as Tuerdi said. But for this specific area, we have achieved quite a good performance for a lab system. So if I move, I think Tuerdi mentioned this. It's very hard to get beam time, and it's expensive when you do it as for the industry. And when you get there, the instruments or the experiments must be perfect. You don't want to waste your slot when you are at the synchrotron. And there I believe we can do quite a lot to prepare, to see that you have the right experiment set up. And then when you go there, you can be well on your way. The Swiss light source Tomcat beamline is the classic zebrafish head, where you get excellent image quality and very, very short scan times. But still, we can achieve single micron resolution CT. That means that we're on a 1,000th of a millimeter. We can see single cells in the eye here. But of course, it takes longer time. When it's minutes at the beamline, we need hours still. But we'll get there. And what is it we're doing here? Most lab-based CT, micro CT, use what we say absorption contrast, that we get a shadow pretty much on the detector of the image. The photons going through the sample are absorbed, and we detect the photons going through it. So that's very good for high density materials. Like if we see a classic 2D lung X-ray, we see the bone inside the body quite well, while the soft tissue is quite blurry. And here we add in our system something called phase contrast. The difference we can see here in the image with the same image, same sample with absorption contrast, and then we have added this information from the phase contrast. And here we can actually see single hairs on this wasp. And what we do is we use a property that in the X-ray or in any photon light, any light, that we have refraction in when the photons encounter density differences. And by moving, usually we would have put the detector very close to get good resolution, but we move the detector quite a bit away from the sample itself to be able to detect the signal from the refraction on single pixels in the detector. So we don't move it while scanning. We decide the distance between this propagation distance between the sample and the detector, and then we do the scan as Tuerdi said, 180, or we usually do 360 degrees. All right, was it something came up? No. And then after that, it's all about software. We do our own reconstruction software, where we translate these 2D images with the phase contrast information through algorithms into the 3D geometry, 3D slices. And we also handle artifacts that are generated because of this. That's errors in the images that we need to handle. This leg of a wasp. This is the absorption image we get, and then we add the phase information. And it also says that no staining. It's very usual that when we have this low density, low contrast sample materials, we can enhance the contrast by staining or adding something with higher contrast. But this is with absolutely no additives, additional staining. Okay, we saw the instrument from the outside. I can move back to that slightly. Here, our first installed instrument at DTU in Copenhagen. And now we also have at University Basel and Karolinska University. And what we see here is actually the apple here is the object, and up there is a detector. So this is what the user usually interacts with, and of course the interface. And it's plug and play. You connect internet and 3-phase power source, and you're up and running. I move back to this then. As Tuerdi said, we have an X-ray source, and for this we use the Exciscope metal jet. It's a Swedish product, and the extremely good thing with that is that we have very high power. We get up to 250 watts of power, and traditional sources may reach 15 to 20, and that can be translated to that we get better images, but also faster. We can do things faster. So we have the X-ray source. We have where we rotate the object, and we can also move it a little on top to get the right region of interest in the sample, because usually we don't see it until we do the first images, what we actually want to see inside. And we have quite a big volume that we can scan, but also, as Tuerdi said, that bigger volume usually leads to less resolution. So that's a trade-off we get. But we can scan very small things as well. There's a motion system that we use for achieving this distance between the detector, the source, the object, and the detector. So we can move this depending on what we want to see in the image. And then we can adjust the height. So we can scan different sections of the same object, or we can scan a lot of objects stacked on top of each other. And then we also have the detectors on this end. This is our high resolution in-house developed detector, and then there's a standard flat, larger field of view detector here. But it's what you need inside. We also have an in-situ device, so we can provide air or gas or liquid to an experiment. So this is a slave rotary unit that will move in sync with the object movement. But of course, adding things up here will decrease the possible volume or the scan height. If we look at the detector, we have this in-house development. We have we can practically say 3 detectors with different magnification. We have a 10x objective, a 4x, and a 2x, giving us a field of view, how much we can detect on the detector itself, by 1.3 times 1.3 up to 6.5 to 6.5 times 6.5 square millimeters. So it's quite small in the front there, but with our larger field of view detector, we have a 66 times 66 field of view at the detector, I should say. When we start to move things between here, we get the magnifications. Depending on where we put the object relative to the detector, the field of view will decrease or increase. Okay, so that's the inside. A little bit about what we can see. I mentioned low SED or low density, or also in biomedical we use, say, soft tissue. But there are a lot of different applications that this is really useful for. We can do, this is a wood, this is a toothpick actually, food and packaging, archaeology, non-destructive analysis of mummy hand we have done. Material science, there's a lot of plastics of polymers out there. Food science, agriculture, biomedical, and then we also have clinical, and there we target what we call virtual histology. So many, even though we have to focus on as we cannot do everything. This is saying that we can work with low density materials gives us quite a big range of application. So this toothpick, you see here is about 0.5 millimeter, and we do this scan in 10 seconds. That means all the projections around the toothpick in 10 seconds. And we can see about 20 to 30 micrometer structures inside here. And that's very interesting for a lab instrument to achieve very short scan times, because we can do 4D or time resolved imaging. And I think I have a good example of that here. Let's see if this works. Yes, Tuerdi mentioned baking. So this is a rising dough, actually, where we do 1 minute scans over a 18-minute time period. We do 7 scans, and we can see the air bubbles rise inside the dough. Really interesting, and this could be applied for many different applications to see things over time. And you have your instruments in the lab, so you don't have to go next week to the synchrotron. Food and packaging, different examples here. A milk package we have here with you know, the layers in the milk carton. We can investigate how that is glued together. I mentioned archaeology. We've done this scan of a mummified hand. We can see different sections of the hand. The nail here. If we move on to material science, we have a golf club here with carbon fiber composite. And here is an air gap, so it's a fault in production. But carbon fiber and air are very low density materials. So it's in a traditional absorption based micro CT, this can be tricky to see. And also to that, we thanks to our high power lab source, X-ray source, we can do this quite fast. Sorry about that. Polymers. This is an implant. We can investigate how it has grown into the tissue. Food and science. We have a Christmas tree bud here. Let's see if it moves. Ah! There we go. And also a rosebud on the other side, a rose hip. So we can see really distinguish different features of the rose hip inside the slices. And this is one of our great visions, that we will enter the clinical market to support in what we call virtual histology. In classic histology, you take the sample and you do preparations and paraffin embedded, and then you do very thin slices. and do staining and look at them in a standard microscope. And in this case, this is actually the slice taken out from a puck where you mount a paraffin embedded sample or tissue. And then if we can play this, this is actually the same puck with the same tissue, and it's just the slice has been taken from the top, and then we scan the rest. So we can see below what pathologists could see in the microscope. We could here see that there were more things below. This is a very interesting area, and there are a lot of research going on here. And then another example of histology. And what we want to show here is that in both these images we can actually see, or an expert can what do you call it? Interpret what is what in between those images. Tuerdi also mentioned that one thing about micro CT and when we get up in resolution and want to have a larger field of view, it will be quite computational, quite a computational challenge. So we have actually developed a cloud reconstruction software. So when we have scanned a sample, it's immediately sent to the cloud. It's a Microsoft Azure cloud, and there we perform the reconstruction itself. So there's no IT infrastructure required on site. And the obvious benefits are listed here, that we have infinite storage, these maybe 60 to 100 gigabytes of data for a single set. And then we start doing post-processing. That can be, it can be expanded indefinitely. But also for the computing power, that when we want to have more computing power, we add another GPU to the reconstruction process. And then, of course, collaboration, online analysis, remote access. When we scan something here or in Denmark, it's available to users that have the right access. And of course, we can look at the same data from different people. And the final value of this would be that it's always updated. We're always in control of how the acquisition computational power and the software is updated. It's not localized on different systems. And this has been quite a benefit for our customers so far. With that, I think I have, yes, I'm done.
Great, thank you, Lars.
Thank you very much for that.
Thanks for a very nice presentation. I think we have a time for a few questions directly to Lars here, if anyone has questions. So we can open up for that. Dirk, you have one, I see.
Oh, that was very impressive regarding the histology. I worked a little in that field before, and you showed some calcification also. Mainly, this is done by histology is done by standard staining or by antibody staining. How do you look into that? That you could probably stain with antibodies in some way to have something on that you could detect in your matter. Have you planned something for that?
It's been discussed. It's not in the plan right now, but it's a topic that comes up quite often. To start with, we have to move slowly but surely here. There's a new area for the pathologist working with this. So we move one step at a time. We start with just looking at the pucks before staining, before slicing, and we can support to see where the interesting areas are. That we can help there, and then from there we will move on to different areas, to different interests.
I think pathologists are rather conservative in their use. They're working with technologies which are well proven and 100 years old. But I've also seen pathologists working with, I don't know, 30 slices at the time and trying to understand the 3D structure of that. And they have to reconstruct that in their head in the end. Well, now with scanning technologies, I mean, just by photo scanning the slides, you can probably do that in the computer as well. But of course, if you have an undestructive method like yours, that would be a huge advantage. I think.
Is
looking forward to see more of this in the future. Thanks.
Yes, and they are also very busy. To get a time slot to explain what we're doing.
Yeah, thank you. I think Helena has a question also. We can take that.
Hello, Lars. How about thank you for your presentation.
We don't hear you so well, Helena.
Oh, sorry. Thank you for your presentation, Lars. What about are you building the system here in Sweden, or is it done somewhere else?
Built in Sweden.
Yeah. Okay. Yeah.
Yes. So it's built here in Kista.
So first delivery, was it to Denmark, DTU, or?
Yes.
Yeah. Okay.
And then 2 more last year, or very late 22, the first one into DTU. But I visited Basel last Friday, the second installation, and they are really on their way on doing some very interesting research. Both of these facilities are synchrotron users. They know very well what they are looking for, and they wanted to challenge the system as much as possible to see what quality they can get.
Yeah, you have a really impressive imaging there, so I'm really interested in knowing more.
Yeah. Great.
Yep.
Thank you. Yeah, I think if we can take Astrid, you have a question also, please.
Hi, Lars.
Hi.
Yes, maybe it's not more as a question, but I also wanted to highlight that we already have an ongoing collaboration between RISE and Exciscope. So actually last year we got a funding from Vinnova to utilize LSRI techniques for meat analogs, including fat. And then we are just using Lars system, as he's saying, as a screening technology before we go to synchrotron to verify that we're looking at the right samples before we bring them in. And I was also really happy to see that my scaffold are still of some use. So that's my own PhD thesis.
That's
okay, perfect. Thank you. And then I think, we are on time. So I think I leave the word to Helena now, and then we can save the rest of the questions for the last 10 minutes. So please, Helena.
Oh, thank you, Niklas, and thank you for inviting me to this session. I will now see if I can share my screen and get the presentation up. And now I have sort of. So my name is Helena Björk. I work as a project manager at measurement technology at RISE, and I have been working with the initiative to really strengthen our capacity for micro CT, and that has been a focus since I think 2020, at least for me. But if you say in the perspective for RISE, it's more than that, because there has been initiatives from different part. It was joining technology and also casting technology would like to see that we have that kind of equipment. So now it have established a sort of a CT network within RISE and also establishing network outside RISE, and it's always exciting, especially with you, Lars, entering our, what do you say, network as well. So really enjoyed that, and we have a couple of more. So I will tell you a little bit now. Our focus is with batteries, battery analysis lab, and we have actually, I will just start off and tell you, you have seen some of these pictures before. We have actually done the inauguration in actually 3 labs within SEAL. We have one here in Borås, which is the safety lab, but we also have in Säve, Gothenburg, and also at Nykvarn. But I think well, our initiative here is actually a little bit of a collaboration, and it also a little bit focus on additive manufacturing also for CT, and of course sustainable casting. These we believe is the 3 main drivers for developing and also what you say, complement analysis. And we believe that the battery analysis lab has actually an established test method that they use. And we want to be the complement with the CT to do analysis before and after, or specialized analysis for cells or modules. We will see if we can manage to analyze packs, but at least part of them. But then it comes to dimension and weight. But we hope that we can actually be able to bring more knowledge into battery and, of course, additive manufacturing and sustainable casting material. And you all seen a couple of examples from Tuerdi. He showed from battery scanning and also with additive manufacturing. So I think we can actually contribute a lot, especially when it comes to having a lab facility where you can meet and also exchange ideas and do analysis studies. So, and what we see, and you have seen from before in previous, is that we have a lot of what do you say, battery that involves a lot of sectors. We have the energy sector, industry sector, mobility, of course, but also aero and space, electronics, bioeconomy. So we think that we RISE spans over many of these domains, and we think that if we can actually also use CT for analysis, but of course other instruments as well, but we believe that we can actually be a part of the developing technology for batteries. And what happens in Sweden is that we have actually CT instruments all over Sweden in the micro level, but also, of course, the synchrotron in Lund. But if I only speak with the micro level, we have at Luleå, we have one equipment. I believe we have it in Umeå as well, Uppsala, Stockholm. So it's starting to spread, and things also industry has invested in what do you say, scanning capacity, but still it involves scanning of smaller objects. So we at RISE would like to have the capacity to actually scan larger samples. And I have done a little bit of, what do you say, and this is not all the listed here, but I've listed from 2019 to today, and this has been, and it might be even more. I don't know about all of them, but still there's some highlights what happened during the year. So we believe that many industry and also, of course, university had added their competencies in scanning. And I believe we can have actually a good sort of platform of knowledge, building the competence of handling the equipment, of course, but also be able to do analysis for industry and research in Sweden. So there's a good platform here for doing more. And here is a little bit of how we look upon it when it comes to utilizing CT in development work. So, and we have actually analyzed that the need for scanning is mostly for us is in the product and process design phase, but also, of course, it could be actually applicable in the concept phase. And of course, for testing and production launch. And that is why we see that we have the safety lab and we can actually complement each other. So, and of course, the third one is the root cause analysis that spans over every part of the development. I mean, that can also be that we can be a part of root cause analysis for something that has actually broken. So, but mainly, of course, for RISE in the research, it's mainly in the number one phase, but we can actually contribute in all of them. And what we have set up, but this is just preliminary at the moment because we have really a sort of a timeline here, so it's not been set yet, but we hope that we can start during this year. But I give a little bit of what you say. It's we need a decision first, but as you can see, we have it takes a lot of time to do the investment. I mean, to what you say, delivery time is quite long for the equipment, but still we have a plan for at least 2 years to be able to launch it. So, but this is at the moment what we are working through. So. There can be a little bit of push forward, but we hope that we can start during this year. But every decision hasn't been made yet. And what can we offer here? We can offer scanning, as I said before and after test in this toward the safety lab. We can also test by scanning sealing joints in battery casing. We can verify new sealing methods. And also contactors and cable. We can see that we can also scan newly developed batteries, of course. We can also see, we can be that test capacity for industry, academia, and also institute. So we can actually contribute to being a part of, to help others, of course. And we will also gain metrology knowledge since we have a joint collaboration between different departments at RISE. So measurement technology department and also battery expertise is combined here. And of course, others as well, because you can do a lot with the CT scan, of course. And we also have a network with CT competence. So we believe that we have a strong, strong offering from RISE side. So we hope that we can move forward quite soon. And what we are aiming at is really the micro CT level. As you can see, and I noticed that also Tuerdi showed this diagram. So we are actually at the micro level, and we might see if we can get the nano source, but we will check that out. But still, we are focusing in the micro level at the moment. But the goal is also that we can actually take on larger objects. So we hope that this will sort of be a puzzle piece in this CT equipment. And I was going to describe a little bit about the CT technology, but I noticed that Tuerdi made a very good presentation. So my slides here will be a little bit simpler, but as you saw before, we have actually a little bit of, this is a larger system, and the principle is the same, that you have the X-ray source and a turning table, and you will have the detector that will detect the X-ray emissions, and it will be projections for 2D images, and it will reconstruct for 3D, and you will end up here in the left corner for a 3D image. And you always work with the, what do you say, in the pictures you work with pixels, but here you work with voxels. So that will be your reconstructed 3D volume here. So you work with also with the distance between the source and the detector and the object. So, and there's a couple of techniques with the X-ray source, but I won't go into that because that will have another seminar, I think. So, and I'm not the expert, so I leave that to others. But there's a lot of technologies involved in this, but a simple description of tomography. Moving on, and a new initiative that we have actually is not involves the technology itself. It's regarding analysis capacity and also data storage. And this hasn't been set yet, but we have ongoing discussion about how can we actually share data with each other and give what do you say, a good infrastructure on the IT sort of IT level. So I just mentioned it. I got this slide from a colleague of mine, Petri Lomala, and he has shown it. I think you, Niklas, have seen it before, but we would like to see that we can actually, well, not share data, but actually have a smoother interface. So we can actually collaborate a little bit closer with MAX4 and RISE. So if you have any more questions about this, I think Petri, he can show more, but I know that he is in contact with Niklas Lorén, but I think I would like to show it because we have, if we will have our investment for the battery analysis lab, we will actually include that as well, so we can actually share data with each other. So I think that will be interesting, and also, of course, shared development for AI development. And I think that's a critical part here for bringing out more knowledge from CT and also, of course, from MAX4. So I leave now my presentation. I have a little bit more slides, but I will leave them at the moment. And I ask Niklas, am I on time or is it...
Yeah, you have still 5 minutes to go.
Okay, then I can ask if anyone has any question for this initiative for battery analysis lab. I can't see if anyone has any question. Can you see that, Niklas?
No, I'm looking.
Yeah.
So please speak up, or yeah, you can use.
Yeah, I can.
Raise your hand.
I have a couple. Yeah, I can show a little bit about the equipment that we have actually investigating. But since we are, this is an ongoing process, we have done some scans and we visited actually Nikon and we made a test for batteries. And what we're aiming for actually is the largest equipment, as you can see highlighted in pink here. But when we visited London, it was actually another equipment that we utilized, but it was equipped with the same source as you have on the larger system. So it was not like tailor-made, like made for the it was a combination of the 30 and 40 series that we tested on. But here you can see a glimpse of what we saw there, and you get a feeling of how big it is. And here you see the turning table, and we have the X-ray source here and the detector here. I had to take more photos because I couldn't manage to get it all in the same picture, but I think you can get a feeling of how large it is. And also here you can see the opening door, and you can actually enter inside. So and this was a C45 source. It was the largest source that they had, and we did actually some tests here, and it involves battery for everything here. And as you can see, you have actually scanning time here as a result, and also resolution, what we got. And here we actually scanned a whole module with a 450 kV rotating target, and it took actually 16 hours. And we got the resolution for almost 70 micrometers. So we had a lot of time there, but still we got the whole module. And we also did some scanning for 7 hours, and we got the middle region. So when it comes to battery, it's quite dense material here. And well, depending on how good resolution you want, you can actually see. It takes a lot of time actually, but still, if you're going through the smaller one, it's not so. It's quite fast, but not as fast. Of course, if you talk about organic material, that's much faster. So, what Lars showed, that was quite fast, I think. So, battery is dense. So. And here also we did a test for AA batteries. Also, that's kind of a smaller one that you use in an electrical toothbrush, and that's took us well 50 minutes, and we got down to 22. So I think that describes a little bit what we are looking into. And here is the scanning result for the whole module, at least the top of it. So, and we got also the projection here with almost 10,000 per panel, and a little bit of the setting that was utilized for this type of scanning. So those of you who have done some scannings are pretty familiar with it. So there is what do you say? It's a key factor is a combination of different type of setting. It's both how to set up in the machine, but also, of course, how much voltage, current, and also filtering. So, but at least you can get a glimpse of how the results from the scanning. So I will end here now. So hopefully I have some question here, and I end my presentation. And I thank you, Niklas, for inviting me here. So really interesting learning more about Tuerdi's work and also what Lars is doing. So thank you.
Okay, thank you, Helena. So I think with that, first, I would like to thank all the speakers. So Tuerdi, Lars, and Helena, thanks a lot for your contributions and for the very nice presentations. I think now we have a little bit time for questions to Helena, Lars, and Tuerdi. So please feel free to put questions. So Helena, you have a question directly.
Yeah, I had one for Lars. What do you use any type of filtering for your application, or?
A little bit aluminum filters. We can use other, but for our use case, usually thin aluminum filters when we have denser materials. So
yeah. Further questions? Otherwise, I have one for you, Lars. I thought that this cloud reconstruction was very interesting. I mean, what do you have for cost models there? Is that included when you buy the machine, or do you pay a yearly fee to get access to that? Or I mean, there must be some limitations somewhere, I guess, in terms of storage room and so on as well. Or how is the business model around that, so to say?
We have a separate license on that for a certain amount of computational power or capacity and storage capacity. And then if you exceed that, you add to it. But it's we believe it's well comparable to run the IT infrastructure that's required to do this.
Okay, but you have this cluster yourself, so to say, at your place, basically, or you rent that somewhere?
We use Microsoft Azure.
Okay.
We could port it to others as well, but we don't run it ourselves.
Okay, thanks. Helena?
Yes, Lars, do you utilize Azure also for computational power? I mean, a
Yes.
platform. Yeah.
Yes. So we're doing a development now that will use even more gigabytes. And someone asked, how are you going to manage that? Oh, we just throw in another GPU.
Okay. Yeah.
We will see how that works.
But is that also, is it container or containers, or is it
containers?
Yeah.
Yes, I didn't mention before that of course we do imaging as a service here in Kista on our lab instrument or in-house instrument, or if there are people interested in trying out the system or doing scans for a project.
Okay. So then we can contact you, Lars, if
yes.
we are interested. Okay, that's good. That's good to know. Yeah, further questions? I have one for you, Helena. I mean, so basically you are planning for, there's something there you can scan really big objects, let's say, in terms of 50 centimeters or in that order. Okay. Yeah.
But I mean, if it works well, I think that we might need to see if we can invest in further technologies as well. It would be, but it costs a lot, so we do need funding for it. But I believe still that there is a kind of a need for both the smaller equipment as well, because once you have started with the CT technology, you want to know more. So that's, but that's on the wish list.
Okay, but that's good to know. I should also say that we have a little bit a system that I think is Malte Wallmeyer, who is in charge of the lab CT that we have in Stockholm. Yeah, it's a little bit older, but it's still a very good machine. So I mean, you can also talk to Malte if you would like to get help. I think. Yeah, there are different options then. I think in terms of speed, Lars' machine is very nice also, I think, and what we have internally is more for slow scans, I guess, but still good resolution. But Lars, what type of resolution can you get from your machine? Is it in the order of 1 micrometer? I think you had on one of the graphs you said.
Yes.
Yeah. So from 1 micrometers and up, you can say,
Yeah, exactly.
Okay. Yeah. And the biggest size for the time being, that would be, is that 64 times 64 millimeters? Is that the maximum size of the sample, or could you have bigger samples as well?
The samples can be bigger, but the field of view will be affected by how far away you must move the detector from the center of rotation or the object.
Okay.
So we 66 times 66 is what the detector size is, and we will always be quite far, a bit away from it. So 40 times 40 is more reasonable.
Realistic field of view, so to say.
Yeah, but then we can move the detector to get the offset scan, and we can also move the object and then stitch it.
Okay, and then you can get bigger. Okay.
Yes, and a lot more data.
Yeah, yeah, that's the advantage and the drawback in a way. Yes, good. Do we have some?
I have a question for Tuerdi. What's going on in the image sort of software development and analysis? Have you it's a quite a large question, but do you have any?
And for processing, normally we have our own routines, which is using a Python or MATLAB-based routines. And also in the facilities, they also provide the pipelines, which is very well integrated with also like as Lars mentioned, like there's everything in the facility cloud will helps to reconstruct, and then we can get this reconstructed image ourselves working still at using the facility, the networks, or we can extract it ourselves using this home cooked or facility prepared pipelines.
Yeah. Okay. Nice.
Good. Thanks. Some more questions? Okay, otherwise I think we end here. So again, I would like to thank everyone that has been listening to the webinar. And I would like to thank Lars from outside, so say outside RISE from Exciscope joining us. It was really nice. And then also Tuerdi and Helena for your very nice presentation. And I also would like to thank Jessica, our communicator, for helping us to set up this. And with this, I would like to thank you all and wish you a very nice day. So thank you. See you.
Thank you.
Thank you.
Thank you.
Bye.
Bye-bye.
Bye-bye.
Thank you.